In this example, we will apply the conservation of mass principle to a diffuser operating at steady state. A diffuser is a device that reduces flow velocity by changing area. An incompressible fluid with a density of 1,000 kilograms per meter cubed enters a diffuser at a velocity of 10 meters per second through an area of 0.1 meters squared. At the exit, the density is equal to the inlet density, 1,000 kilograms per meter cubed, because the fluid is incompressible. The exit area is 1 meter squared, 10 times the inlet area. We're going to find the exit flow velocity. Let's start by defining our system. We start with the schematic of the diffuser, a flow path with an increasing area. The inlet is labeled Station 1 and the outlet is labeled Station 2. Next, we define our system boundary as the volume enclosed by the walls of the diffuser. We will apply the conservation equations to this control volume. Mass crosses the system boundary at two locations, Station 1 and Station 2. The next step in solving an open system is to apply the conservation of mass principle. This principle enables us to write a mass balance in terms of the system that we have defined. The rate of change of mass contained within the control volume is equal to the sum of mass flows entering the control volume minus the sum of mass flows exiting the control volume. For steady operation, the time derivatives are zero. In other words, the mass of fluid within the control volume does not change with time. The result of the mass balance is that the mass flow into the system at Station 1 must be equal to the mass flow out of the system at Station 2. Let's continue by evaluating the mass flow rate at each station. For a one-dimensional flow, the mass flow is equal to the density times the velocity times the area. We can write this for both Station 1 and Station 2. Substituting this result into the mass balance, we see that the density times velocity times area at Station 1 must be equal to the density times velocity times area at Station 2. We can solve this equation for the velocity at Station 2, which is what we are looking for in this problem. The velocity at Station 2 is equal to the density at 1 divided by the density at 2 times area 1 divided by area 2 times velocity 1. Substituting the values given in the problem statement, we have 1,000 kilograms per meter cubed divided by 1,000 kilograms per meter cubed times 0.1 meters squared divided by 1 meter squared times 10 meters per second. The result is that the exit velocity is 1 meter per second, a 10 times reduction of the inlet velocity. For an incompressible flow, the ratio of inlet and exit velocities is equal to the inverse ratio of the areas because the densities cancel out. That concludes the example. Thanks for tuning in and have a great day.